Hi everyone, I'm Daniel Köhn from the Institute of Geoscience at Christian Albrechts University Kiel. The intensification of storm surges due to climate change require non-invasive assessment methods to estimate the state of coastal protection. Today I want to show you the potential of seismic SH for waveform inversion for high-resolution imaging of sea dikes. The study area is the Tümlauer-Koog sea dike located at the western coast of northern Germany. Here are some impressions from the acquisition of the shear wave data. We employed a seismic line from the land side over the peak of the dike down to the shoreline on the seaside of the dike. To excitate shear waves, we used a shear wave anchor and a simple hammer drop on one side of the anchor. In total, the acquisition geometry consists of 48 shots and receivers with a spacing of 1 meter. Shot 4 to 21 are excitated on the land side, while shot 26 to 48 are on the seaside. Notice also that the sea-dike can be very well approximated as a 2D medium, which extends almost to infinity, as you can see in this picture. Therefore, wave propagation within the dike can be well approximated by the 2D SH problem, which we will solve numerically to predict the wave field for a given subsurface model. Here you can see the shot gather for shot point number 6 on the land side of the dike. Beside the direct and refracted wave, the wave field is dominated by a quite dispersive laugh wave, which is reflected by the pavements in front and behind the dike. So you can see here the pavements and they reflect the surface waves here. The significant surface topography of the sea dike makes the for waveform inversion of the dataset quite challenging, because the topography has to be incorporated into the seismic modeling code in order to correctly predict the laugh wave field and then fit the field data within the waveform inversion to recover a high-resolution model of the subsurface. So there are different approaches to solve this issue. In this talk I want to focus on two of these solutions. First, we can restrict the waveform inversion to the shots and receivers on the land and seaside of the dike. And because the dike slope is approximately constant, we don't have to deal with the topography at all, but can rely on our seismic modeling code with a flat free surface boundary condition. So here you can see the initial models for the waveform inversion based on first arrival travel time tomography. The subsurface can be approximated by a simple 1D medium consisting of a low velocity layer with a thickness of about 1 meter over a homogeneous half space. The velocities on the seaside are systematically smaller than on the land side by approximately 30 meters per second. To correctly describe the laugh wave dispersion, a viscoelastic model is required. We conducted multiple for waveform inversion runs using different homogeneous QS models as passive model parameters, which are not updated during the inversion, and then evaluated the final data misfit. While on the land side of the dike, a distinct minimum occurs for QS equals 50, we have two possible optimum QS models for the seaside, QS equals 10 and QS equals 20. Both waveform inversion models differ only in the smoothness of the resulting VS models. So for the following discussion of the waveform inversion results, we decided to focus on the QS equals 20 waveform inversion result. To mitigate the nonlinearity of the inverse problem, we use a sequential frequency inversion approach by inverting 8 low-pass filtered frequency bands with increasing maximum corner frequencies of 15, 20, 30, 40, 50, 60, 70 and 80 Hz. Compared to the first arrival travel time tomography model, the waveform inversion adds additional small-scale features as well as horizontal and tilted layers on both sides of the dike. Especially I want to emphasize this high velocity layer at the base of the dike, which can be seen on the land and the seaside, as well as this thin high velocity layer just below the first low velocity layer. This high velocity layer is significantly disturbed near the shoreline at the seaside of the dike. Notice also these small near surface velocity anomalies. To evaluate the quality of the inversion result, we compared the model data for the final waveform inversion result, shown here in red, with the field data, shown in black. Besides some remaining minor misfits, the overall data fit is very good. So we inverted the data separately for the land and seaside, and this approach seemed to work quite well. However, the disadvantage of this approach is that we cannot resolve the structures in the core of the dike. In order to invert the whole data set across the dike, we cannot ignore the surface topography any longer. To discuss the issues with the surface topography a little bit more, I borrowed another problem with significant topography from our PhD student Manuel Zolcho, who will present his results in a talk on October the 19th. In order to use this model in a computer to solve the viscoelastic equations of motions, we have to discretize it. As you can see, when discretizing the model on a Cartesian grid with a spatial grid point distance of 20 centimeters, the surface topography is approximated by these artificial steps. You might think, what's the big issue? Well, if you try to compute seismic wave fields with such undersampled models, significant love wave reflections and diffractions will occur. During the waveform inversion, these artifacts in the modeled wave field will prohibit a successful convergence of the inversion. So what can we do about this problem? There exist two very sophisticated mathematical solutions and one, let's say, not very sophisticated but quite effective solution. Let's first shortly discuss the two mathematically ambitious approaches. So first, you can deform the surface boundary of the Cartesian mesh according to the surface topography. This can be achieved by the so-called transfinite interpolation. If you're interested in details, I've linked a Jupyter notebook from my seismic modeling lectures regarding this topic. The other approach is to discretize the model with a triangular instead of a Cartesian mesh for a better representation of the surface topography. This mesh can then be used to solve the forward problem with a finite element or finite volume method. Now, what is the not very sophisticated approach? Very simple, you oversample the subsurface model. At the top you see the spatially undersampled model with 20 cm grid point distance. If we oversample the model with a grid point distance of 5 cm, the discretization artifacts are significantly mitigated and therefore also the related impact on the modeled love waveforms. This approach is quite easy to implement because we don't have to change anything in our modeling code but only change the model discretization. An obvious disadvantage of this approach are significantly longer computation times for the wave field modeling due to the larger spatial grid. But if you have enough computation power, as we have at the Kiel University, this is actually not an issue. So oversampling is one part of this approach. The other is to consider how to implement an accurate free surface boundary condition. This can be achieved by assuming vacuum properties above the surface topography and then apply some special numerical tricks in order to avoid numerical singularities in the finite difference code. For further details, I added a link to a very nice paper by Pan et al. 2018. So now we can accurately model lava wave propagation in the presence of strong surface topography and run our waveform inversion for the whole dataset. This time we applied a multi-parameter SH waveform inversion optimizing the S-wave velocity and density model, so I plotted the density model this time. We can recognize similar features as in the previous inversion result. A low density layer near the surface is followed by a thin high density layer below. So we see this on the land and on the seaside. And these two layers are disturbed by a low density anomaly near the shoreline. Compared to the previous inversion result, we are now also able to resolve the core of the dike, which consists of a bunch of high-density layers with values of up to 2,200 kg per cubic meters. To identify possible correlations of the waveform inversion result with lithological features, we compare the density model with geological borehole interpretations. The pink color here denotes marine clay, while the yellow colors represent sand. In some cases, there seemed to be a correlation of sand with high density layers, as you can see, for example, over here. In other cases, we cannot really correlate the boreholes with the waveform inversion result. Now let me summarize the essence of this talk. So first of all, we demonstrated the potential of SH waveform inversion as a tool for evaluating the S-wave velocity and also the density structure of a sea-dike. The waveform inversion result can be partly correlated with lithological structures. Of course, you always have to be careful when doing such comparisons. So you have physical parameters on the one side and a geological interpretation on the other side. So you're actually comparing apples to oranges. Now, before wrapping up my talk, I want to give a short outlook about our next steps related to sea-dike for waveform inversion applications. So the obvious next step is to apply a 2D multi-parameter VSQS waveform inversion. And from this VSQS inversion, we can possibly derive the influence of water saturation and compare this also with 2D geoelectrical measurements. Maybe it's also useful to incorporate not only SH data but also PS data into the waveform inversion, so to get really a better understanding about the water saturation inside the dike. Another interesting approach would be to apply time-lapse VSQS inversion to see what are actually the changes within the dike. Finally, we want to apply the waveform inversion also to ambient noise data, and I want to show you the potential of this approach on the next two slides. So far we used only active source seismic data for the waveform inversion. However, to monitor changes in the dike, it would be much more convenient to use passive data for the inversion. In September 2017, we recorded some ambient noise data with the small array on top of the dike. Here you see amplitude spectra covering the time from September the 8th to September the 22nd. Notice this significant increase of the amplitude spectra on September the 14th due to a storm surge. From the ambient noise data, we computed Green's functions, seen here in red, and compared them with the shot gathers of the active source seismic data in black. The ambient noise-based seismograms can fit the active source lava wave data quite well. So we are very confident that we can use this passive seismic data for monitoring changes within the dike based on baseline active source waveform inversion results. So this was just a short outlook. Finally, I want to thank the usual suspects for their financial support, the Computing Center at Kiel University, and finally you for your attention. Thank you very much.